Today's lesson is on uniform circular motion. Imagine you have a ball. It is attached to a string and it is being rotated counterclockwise in a circle. The ball is moving with the constant speed as it goes around in the circle, and the ball is accelerating because it is always changing direction or continually changing direction. Now, when this ball moves around in a circle, there is a special force acting on it. It is called the centripetal force, and the centripetal force acts on any object that is moving in a circle. And the centripetal force always acts inward from your direction of motion, or inward from your circular path. So when the ball is in position 1, there is a centripetal force that is acting inward, or in this case, down. In case 2, there is a centripetal force that is acting inward, or to the east or right. In case 3, there is a centripetal force acting inward, or in this case, up. And in case 4, the centripetal force acts inward, or to the left. Now, when an object moves in uniform circular motion, there is also something called a tangential velocity that is acting on your object. In my example here, in situation 1, the tangential speed acts in this direction, as I note with red, so acting to the left. In case 2, your tangential speed is acting down. In case 3, it is acting to the right. And in case 4, my tangential speed is acting up. Your tangential speed is the direction that your ball would go in, or object would go in, if the centripetal force were to stop. In this case, the object that is creating the centripetal force is the string that is attached to the ball. So in case 1, if the string were to break, which I'll show with green here, the ball would take off in the direction of the tangential speed, or in the red line. In case 2, if the string were to break, the ball would go down. In case 3, if the string were to break at that point, the ball would take off to the right. And in case 4, if the string were to break, the ball would go up. When you look at this picture, you'll notice that there is a relationship between the tangential speed and the centripetal force. And that is, the tangential speed and the centripetal force are perpendicular to each other, or at a right angle to each other, which I'm showing here in the color orange. The last thing I want to fit into this diagram is where the acceleration fits in, because the ball is accelerating. It is moving at a constant speed, but everywhere along its circular path it's changing direction. So remember, acceleration looks at your change in velocity over your change in time, and velocity is not only your speed but your direction. So if your direction changes, then you are accelerating. So where is the direction of the acceleration? Well, according to Newton's second law of motion, which says the sum of the forces is equal to ma, it turns out that what that is saying is whatever direction your net force is in, that's the direction of your acceleration. Now, a little bit later, I'm going to show you how your centripetal force is your net force. So whatever direction your centripetal force is in, that's the direction of your acceleration. And we're going to call the acceleration in this case centripetal acceleration. So with yellow, I want to show you how the centripetal acceleration is in the direction of my centripetal force. It's my A sub C here. In case 3 with yellow, my A sub C is acting up. In case 4, my A sub C, or centripetal acceleration, is acting to the left. Okay, so there's a lot going on with this picture, so we're going to move on from here. All right, now Newton's second law of motion says the sum of the forces acting on an object is equal to the mass of that object times the object's acceleration. In uniform circular motion, the sum of the forces acting on an object is called your centripetal force, and that's equal to the object's mass multiplied by that object's acceleration, which is now called centripetal acceleration. The direction of your centripetal force is always inward from your circular path, and the direction of your centripetal acceleration is always inward from your circular path. Now, your centripetal acceleration has a formula as well, and that's equal to your tangential speed squared divided by the radius of your circle. So if we plug in our expression for centripetal acceleration here into Newton's second law, I get centripetal force is equal to m, or the mass, times your tangential speed squared all over the radius of your circle. There is also a formula for your tangential speed. Now, speed of anything is just equal to your total distance traveled divided by your total time to travel that distance. Well, if you are moving in a circle, what is the total distance traveled when you move in one whole revolution? The distance for one whole revolution is equal to the circumference of that circle. And the circumference of a circle, the formula for that is 2 times pi times the radius of your circle. And the time that it takes to go around in that circle is called, we're going to give a capital T here, that is called the period or the time to go around in one revolution, and the unit for that is seconds. All right, now I want to talk with you a little bit about period, and that again is the time it takes for an object to make one revolution. So let's say, for example, we have the sun. Here's the sun. And let's say we have the Earth, which is orbiting the sun. And the Earth orbits the sun. And my question to you is, what is the period of the Earth as it revolves around the sun? What is the time it takes for the Earth to make one whole revolution? And the answer to that is, of course, 365.25 days. That is the period for the Earth to revolve around the sun. All right, now going back to our equation, which is tangential speed is equal to 2 pi r over t, or period. What I would like to do now is take that expression and substitute that in to Newton's second law of motion here. And that will look quite interesting. We're going to get my centripetal force, which is the sum of the forces acting on an object moving in uniform circular motion, multiplied by the object's mass, multiplied by the tangential speed, which is 2 pi r over the period, and we're going to square all of that because that's the tangential speed, all over the radius. And so this is another expression we can use for Newton's second law when we have an object in uniform circular motion. All right, let's draw some free body diagrams of objects moving in uniform circular motion. There are two types we need to know about. The first one is when an object is moving in a vertical circle. And this is something I already showed you. So we have an object in situation 1, situation 2, situation 3, situation 4. And it's rotating, let's say, counterclockwise. Okay. Now, what is the free body diagram in each case? In case 1, there is a tension in the rope acting down. In case 2, the tension is to the right. In case 3, the tension is up, and in case 4, the tension is to the left. But there is another force acting here, and that is the weight of the ball. So in case 1, The weight, by the way, is always down. So in case 1, the weight's down. In case 2, in red here, my weight is down. In case 3, my weight is down. And in case 4, my weight is down. Now, my centripetal force in case 1 is the sum of the forces acting on the ball. So that would be tension. Now let's go ahead, if we make up positive, that would be negative, let's rewrite that, a negative tension minus a negative mg. Those are the sum of my forces acting on the ball, and that's equal to a mass multiplied by a negative centripetal acceleration, because the centripetal acceleration is also acting down in case 1. So this is the centripetal force in case 1. What about the centripetal force in case 2? That's going to be, let's make right positive. So that will be my tension, which is positive. And this is the only thing that is acting inward. So I'm only interested in the forces acting along the plane of where the centripetal force would act. So that's just equal to ma sub c. We're not interested in the weight in this case. My centripetal force in the third is a little bit more interesting. I'm going to have a positive tension minus an mg is equal to a mass times my centripetal acceleration. My centripetal acceleration will always be inward, so it will be acting upward, and that therefore it will be positive. And lastly, my centripetal force in the fourth position is going to be a negative t is equal to a mass times a negative a sub c, because my centripetal acceleration is acting to the left, and so is my tension is acting to the left, and that is in the negative direction. What about horizontal circles, objects moving in a horizontal circle? So I have some ball that's moving horizontal in this diagram here. And we have two forces acting on this ball. The first one is the weight acting down, mg. And the other one is the force of tension from the rope that's holding onto the ball. Now, interestingly enough, you can see that the force of tension is not exactly vertical, it's not exactly horizontal. So this means that my force of tension will need to be resolved into components. So I will have a horizontal component, and I will have a, let's get a different color here, a vertical component. My vertical component we can call Ty, and my horizontal component we can call Tx, and my purple one here, I have a little arrow up. Okay, so there's our diagram. Also, though, we also have an angle, don't we? Let's see if I can fit that in there. We have an angle that I might be interested in here, and we'll call that theta, and so we also have an angle. Now, in this diagram, which one of these forces is the centripetal force? Remember, the centripetal force is the force that acts inward from the circular path. And there's only one force in this case, and that is Tx. Your Tx, let's make right positive. Your Tx is your forces, your sum of your forces in your x direction. In this case, that's also your centripetal force. It's equal to the mass of the ball multiplied by the ball's centripetal acceleration. Now recall that your centripetal acceleration is also equal to your tangential speed squared over r, and also your centripetal force then would be equal to the mass multiplied by 2 pi r over period squared over r. Also recall that your centripetal force in this case is the tension in the x direction, or the component of the horizontal component of the tension in the rope. Now let's go back to my picture and take a look at how we could find Tx using a little bit of trigonometry. And recall that your Tx, which is your adjacent over your hypotenuse of t, is going to be cosine theta, or we can say Tx is equal to the tension in the rope times cosine theta. So if we knew the tension in the rope and we knew the angle, we should be able to find T sub x and therefore find the centripetal force value.